Carbon dioxide, it's what makes your carbonated drinks yummy. That process is really very difficult to do because, as you know, carbon dioxide doesn't dissolve to water as easily. In fact, it's not soluble to water. It has very poor solubility. It prefers to leave water. Case in point, if you open your soda can for too long, that fizziness feeling will just eventually run out. So in order to push the carbon dioxide in your soda, what manufacturers do is they cool down your soda at sub-zero temperatures and then pressurize that can and really embed that carbon dioxide in. Now, what happens is that when carbon dioxide dissolves in water forcefully, it creates a very acidic soda. So you'll form carbonic acid. And we know that carbonic acid is unstable. Eventually, it's always going to resort to the direction to the right. Your carbon dioxide is always going to leave water, and so carbon dioxide comes out. Why am I talking about this? Because we can actually predict molecules if it is soluble to water or not. And that's very important in allied health. You guys, or in the drug companies, in order to figure out whether the drug that they have created is easily absorbable or can be dissolved easily into the bodies. And so that's the opening of this chapter. This is what this new chapter is all about. Can we predict whether the molecule is polar or not? There's several ways in order to do that. And so it will start off by looking at the molecular shape of your molecule. So for CO2, last week we discussed about drawing or knowing how to write the Lewis structure of carbon dioxide, and we said that, oh, it would look like this, okay? So we have carbon having 4 bonding pairs, and then your oxygen will have 2 bonding pairs and 2 lone pairs. So this is what the Lewis structure of your molecule, carbon dioxide, will look like. Okay, but that's not the end of it. This is actually a 2D representation of a 3D molecule. What is the shape of this molecule? You'll eventually find out in this new video clip that, in this first video clip that I'm going to show you, that this shape is actually a linear. So this Lewis structure is actually a good representation of what the molecule carbon dioxide will look like. Okay, so it's just so happened that for this molecule, this 2D representation is a good representation of a 3D molecule. I'm sorry, it should be carbon right here. Okay, so we need to know the shape. Now that we know the shape, then we need to know the ability between these two atoms, the sharing capability of these two atoms. Who is greedier than the other? And we're going to figure that out by looking at the electronegativity property of each of the atoms that is sharing the bond. Electronegativity. Okay, this is just a more technical term, but in layman's word, who is greedier? Okay, so here this tells you like carbon here is loaning 2 electrons to oxygen. At the same time, it's also borrowing oxygen electrons, 2 electrons from your oxygen. Okay, so this is a typical covalent bonding. But who is keeping these electrons longer? Okay, it's kind of like a car. So this is a shared property, communal property by the couple. But there will be times wherein one will use the car at a much longer period and duration than the other spouse. And so who is keeping this shared electrons closer to its orbit for a long period of time or for a duration of time? We're going to look at the electronegativity, and that's what the 2 video clips is about. All right, so the next step, so you're going to find out here eventually that oxygen is actually greedier than carbon. And so it's going to keep the oxygen electrons closer to its orbit, and that's what makes this side partially negative. Okay, So the next step, oh, by the way, guys, what we're talking about there is eventually is bond polarity. So that will tell you that this molecule, because they are not sharing the electrons equally, one is greedier than the other. That means this particular bond exhibited between carbon and oxygen is going to be polar. Kind of like magnets. You know, you have some polarity in the magnets. There's a positive and negative charge when you're dealing with magnets. Or when you have a battery, there's always a positive pole and a negative pole. So think of that polarity between the bonds, okay? So this bond is polar because oxygen is greedier. It just so happened that on the left side, it's also an oxygen atom, and therefore this is also polar. Okay, now on the third video clip, or third part of the series, is to finally figure out whether this molecule is polar or not. We call this the molecular polarity. If it is polar, then that molecule will dissolve in solvents that are polar. Water is actually polar, okay? That tells you that if this molecule will be distinguished or will be determined to be polar, chances are it will dissolve in water, which is also polar. Ever hear the terminology like dissolves like? This is it. We're gonna hear this. We're gonna see this now. Like dissolves like. Okay, now if this molecule is determined to be a nonpolar molecule, chances are it's not going to dissolve in water, but rather it can be dissolved in nonpolar solvents. So example of nonpolar solvent will be your gasoline. Okay, so chances are you can dissolve carbon dioxide in gasoline. All right, so let's figure out really quickly. We haven't talked about this. You're going to see this in the video clips, but eventually you're going to see carbon dioxide. Ooh, I am carbon dioxide. I have two sets of twins on both sides, both opposite sides of me. One is greedy, it's really demanding, it's pulling all of my resources. And here's another twin of his on my other side, also pulling at the same magnitude. Where guess what happens? The effect of this pull is just going to be canceled by the effect of the pull to the right. And that makes this molecule non-polar. There is no overall or resulting vector. Okay, so it kind of makes the the electrons balanced out by the pull on the left and the pull on the right. Ergo, carbon dioxide is nonpolar. That means to say that it is highly unlikely to be dissolved in water. And that's what explains why that carbon dioxide fizzles out from your soda drink. Okay, so what? So what if I know polar from non-polar? What's the importance of this? The importance of this is for you guys is quite substantial. Um, know this molecule right here? Probably not, but this is metformin, the main ingredient for the medication that is used for type 2 diabetes. Now, some drugs, maybe you go to CVS or Target, Rite Aid, or Walgreens. Maybe you can do that when this coronavirus social distancing gets lifted off. But eventually, if you would go to the pharmacies, you're going to notice the drug, most of the drugs always contains HCl. And isn't HCl acidic? Doesn't that melt the stomach acid? Yes, but why is it then in your drug? They put that in there to make the drug more soluble to water. Okay, so if you have ions, by putting this, it will make your drug ionized. And so the chances of molecules that are in its ionic form or in its salt form, it will make the drug more soluble to water. Okay, all right. See this drug right here? This is albuterol. This is the main ingredient for that puff, that asthmatic people will take. Okay, what do you think? Predict what is the solubility of this molecule. Is this soluble or not? That's really important. And if it is soluble, which part makes it soluble to water? Okay, that's going to be a topic that will be discussed on Thursday. But for now, let's first figure out whether the molecule is polar or not. Is it soluble to water or not? Eventually, we're going to move on to this really crazy molecules and figuring out whether other properties that is more important other than aside from the polarity. All right, guys, take care.